Okay, so today we are going to start the exercises on factor groups. So this is the first one for 11. So here G is a group and N is a normal subgroup of G. And also suppose that this left coset of N in G, which is an element in this factor group G by N, has order 5 in this group, in this factor group. Then if N has order 14, then what are the possible orders of the element A, of course in the original group G. And also we have to show that each order that we find of A in G can actually occur in some groups, in some concrete example. So let's see the solution. The fact that the order of An, this coset, in the factor group G is 5 immediately tells us something. And this conclusion follows from theorem 4.7. By theorem 4.7, we find that 5 divides the order of A in G. That's because we know from that theorem, this theorem has 3 parts, it's the third part that we are using, which says that the order of the coset An divides the order of the element A. So that's why 5 divides the order of A. So this is one thing. Another thing we can have from this statement is this: since the order of An in the factor group is 5, so the fifth power of An is going to be equal to the identity element of the factor group, which is nothing but the normal subgroup N itself. So we have this as well. Also, this coset of N, which is nothing but the fifth power of the coset An, by the definition of the binary operation in this factor group, we have that. But this is equal to the identity element in the factor group. Which implies what? Which implies that this power of A must belong to N. But okay, why is that so? How does it follow from this that A to the power 5 belongs to N? That's because we know that the left cosets of N form a partition of G. And because these are sets in a partition, so distinct sets should be disjoint. Now we know that A to the power 5 belongs to this coset, A to the power 5n. But that thing is equal to n, so A to the power 5 must be in n. And why does A to the power 5 belong to this coset? That's because any element in this coset is of the form A to the power 5 times something from n, and that something you can choose to be the identity element in n, thus giving you A to the power 5. So A to the power 5 now belongs to n, and now it's given that n itself has order 14. So the 14th power of this element has to be equal to the identity element in n. That is one of the corollaries of Lagrange's theorem. Thus, what is the 14th power of A to the power 5? A to the power 70 by one of the rules of exponents. That is this, and this should be equal to the identity. So this tells us what? This tells us that the order of A in G has to divide the exponent 70. That kind of equation allows us to conclude that. So the order of A should divide 70. Now we have two conditions that the order of A satisfies: this divisibility relation and this one. And based on these two things, now these are the possible values of this order. Thus, that means the order of A now should be a multiple of 5 which also divides 70. And these are the possible values. It can be 5, it can be 10 or 35 or 70 itself. So these are the possible values of the orders of A that we can have from all these things. Now we need to show that all of these orders actually are taken on in some concrete group. So to see that, we are going to take, or rather the author has taken this particular group. Consider the group G equal to this modular group Z70 and N to be the cyclic subgroup generated by phi. Okay. One can verify that the order of n is equal to actually 40. And in fact, let me write down what the elements of n are. The elements of n turn out to just be, so this is the cyclic, keep in mind that in this group the binary operation is addition modulo 70. So you start with 0 and then you have 5 of course, and you keep on considering all the multiples of 5 until you exceed or even reach 70. So these are the things normally we will have. So they are going to be 10, 15, 20, then 25, 30, 35, 40, 45, 50, 55, 60 and 65. If you add one more 5, you are going to get one more 5 to this, then you are going to get 70, which in this group is equal to 0. So these are the elements in n. And you can see, let's count how many elements n has. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that's like this. Also, n is clearly normal in G. That's because G is abelian, so any subgroup is going to be normal in G. Okay, so that is fine. But now, what about the element A? And shall we, what sort of elements A we should choose in this group, in this G, so that we will realize these orders? And those elements are this. Further, one can verify that for each of the elements, so these are the elements 14, 7, 2 and 1. And 1, for each one of them, An has order 5 and this is 5. The order of 7 is 10 in this group. The order of 2 is 35 and the order of 1 is of course 70. So in this concrete group, those things happen. Okay, now one more thing. Seeing that n is normal and its order is 14, we can see that here itself. There is nothing else to do about that. But what about this part? Say you have these elements now. Now, how will you verify that for each such An has order 5? By the way, what is An? First, that question comes now. For example, if your A is 14, then what is 14n? Because the operation is addition modulus 70 and the group is abelian, so we write the left coset An as A plus n. It does not really matter how you write it, but that's how usually we write it. So let us just have a very brief discussion about how one would go about verifying this thing. Say A is 14. Then what about An? An then is 14 plus n. Now when we say 14 plus n, you actually have to add 14 with all these elements in n. That will give you a set, but that is not ordinary addition, but that is addition modulo 70. Now when you do that, you are going to get a coset of n, An, where A is 14. Now when we are saying that An has order 5, that means what? It means that when you calculate this, powers, where in the quotient group G by n, in the factor group G by n, then you have to show that for all positive integers lying between 1 and 4, this is not equal to the identity element in the factor group, but this one is the identity element. When you show this, that guarantees that the order of this in the factor group is 5. Now, in order to show that these powers, none of them is equal to n, there is actually no need to calculate the entire set. You can just simply add 14 with 0, that's it. Keep in mind here also that because the cosets, these powers after all are also going to be some coset of n, right? So these cosets form a partition of this group. So when you have, say, you add 14 with 0, so in this set 14 will be an element. In this set 14 plus n in this coset, when you write that coset down like this, then 14 itself will be an element. Now, do you see 14 here anywhere? No. And you combine that information with the fact that the cosets are disjoint. So definitely 14 plus n itself cannot be equal to n, because distinct cosets cannot have common elements. So if 14 is not there here, then 14 plus n cannot be equal to n. Similarly, you take the second power, that would be what? 14 plus 14, 28. So here you will have 28. That actually gives you 28 plus n. But when you add 28 with 0, in that set you will have 28, which however is absent here. So 28 plus n is also not equal to n. Similarly, you can carry on and show that the third power and the fourth power also, they are not, none of them is equal to n. But the fifth power will be equal to n. To show that, however, you have to calculate all the things. Or you may not calculate all the things. You just note that this will be equal to 70 plus n, because 14 plus 14 plus 14 plus 14 plus 14. But because 70 plus and 70 is just 0, because 0 is an element here, so this coset is nothing but n. There is in fact no need to go through the process of actually finding the elements. So that's how this particular an actually has order 5. And to see that these orders are these numbers, of course you can calculate in the original group, so that will give you these numbers. So this completes the solution. Okay, let us now see the next one. In this one, we have to calculate group tables. Write the group tables for two groups are given and they are factor groups. The first one is the factor group of the dihedral group D8 factored by the cyclic group generated by this rotation R1 180, and the second one is this group U40 factored by the cyclic group generated by the element 3. Yes. Okay, so let's now calculate this. Now there we already have come across the group table of the group D8 itself in one of the examples before. So you have to go back to that example to see that the things that I am going to write actually are true. Now, in order to write something and not just write simply the table itself, you can proceed like this. We know that you know what the elements of D8 are. It has these 4 rotations where the suffixes denote the angles through which you have to rotate, and you are rotating what? You are rotating a square about its central point, if I say so, which is the point of intersection of the 2 diagonals, and about the axis that passes through the plane of the square perpendicularly, like that. Okay, so those rotations, and 4 reflections. F1 is the reflection about a vertical axis, so you flip the square like this. F2 is the reflection about a horizontal axis, you flip the square like this. And F3 and F4 are reflections about the 2 diagonals. You go back to that example, you will see what F3 and F4 specifically are. And we also know what this cyclic group is. Because every, okay, I was thinking it's a reflection. No, it's a rotation, but this particular rotation has order 2 in this group because it's 180. You say the square is in this position. This is of course not a square, but I'm just simply saying 180, another 180, so it comes back to that same state. So that's why it will have order 2, and it is just this. Okay, so now what the first thing you have to figure out is the elements in this. You already know how many elements there will be, and all these elements are going to be cosets of this cyclic subgroup in the group D8. Because the subgroup has order 2 and the original group has order 8, so there will be 8 divided by 2, that is 4 number of cosets, 4 elements in the factor group, and those elements turn out to be these. One can calculate that one can determine that the elements of this factor group are, one element will be the cyclic group itself, which will be the identity element. Then here are the others. R90, R180. So this is the coset of this subgroup by the element R90. That means what you are doing is that the elements of this cyclic subgroup, you are multiplying them, all of them, by R90 from the left side. So this set consists of R90 R0 and R90 R180, and that set turns out to be R90 R0 is going to be R90, of course, and R90 R180 is going to be R270, which you can understand why. A 90-degree rotation followed by a 180-degree rotation. Okay, so we get this. So this is another coset. And note that because of this fact, this set is also equal to R270 R180. Not that we need this, but just simply saying. Okay, then we have F1 R180, and that turns out to have two reflections. One of them is F1 and the other one is F2. Yes. So you can understand that this same can also be expressed as F2 R180. And one more. And that other thing is F3 R180, which turns out to have these two reflections, F3 and F4. Okay, so now we have to form the group table for these cosets. This part we have to erase, so you remember that this is U40 over factored by 3. So you can write, I am not going to write those things. Hence the group table for this factor group is this. So how many cosets are there? 4 cosets. So it should be a 5 by 5 table. One row and one column should be kept for writing the elements themselves, and then the actual table will come after that. Okay, so now we are, first of all, we will just write the elements. R180, then R90, R1, let me write carefully. then F1 are 180 and F3 are 180. So in that order I have written, and I hope that it's visible. R180, R90 are 180, F1 are 180 and F3 are 180. If you want, you can give these elements some other name so that the table looks more neat than this. But here you can directly see what the things are. Okay, so we already know that these things are going to form a group, and in that group, this element is the identity. So we know what the first row and the first column will be. No change. The elements themselves are 90, are 180, F1 are 180 and F3 are 180. And here also F1 are 180, F3 are 180. Okay, then the next thing you are going to calculate is R90 R180 times R90 R180. By the definition of such a product of two cosets, that is R90 R90 R180, but R90 R90 is R180 itself, which belongs to this group, so it is nothing but the subgroup itself. The next one is this times this, which requires us to know what R90 F1 is, and that turns out to be F3. Now you know another fact in a group table, that is that when you are filling in the cells, in each row there is how can I express this? Each element of the group appears exactly once in each row and each column. That's the thing. Let me repeat it. Each element of the group appears in every row and every column exactly once. So we already have R90, R180 here, then R180, F3. So what is the other thing? F1. So you can just simply put that here. And note that we are able to do so because we are not trying to show that this is a group. We already know that this is a group. That's why, excuse me, the table has to be like that. There is one more thing that will help you. Because this group has order 4, it has to be abelian. Any group whose order is at most 5 is abelian. So once you find a row, the correspondingly you also have the column. So now that we have this row, we also have these two entries, and they are going to be this and this. So you have to calculate this. This is also a kind of matrix. No? You calculate the diagonal elements. Then you either calculate the upper triangular of diagonal elements, then the lower triangle is determined, or you calculate the lower triangular elements, then the upper triangle is determined. You do not need to calculate all the things. Next, F1 since F1 is a reflection, so F1 is identity, and identity is in this subgroup R180, so this is R180. Then F1, F3. Now you have F1, F3 and this one, so what else is there? R90. So no need to go looking for that. You already know that it will be R90, and because of this, this one will also be R90, R180, and this one finally is just R180. So that is the group table for this quotient group of the dihedral group D8 by the subgroup, which is the cyclic subgroup generated by the rotation R180. So that is part 1. Then in part 2, our original group is U40, which consists of all the positive integers less than 40 and relatively prime to 40. And the binary operation is multiplication modulo 40. So let us see what the elements are. When you write down the elements, it is easier to calculate the things. So let me just simply copy it from here, just to speed up the process a little. 19, 21, 23, 27, 29, 31, 33, 37 and 39. So whenever you want to calculate, whenever you want to write some such things, some such sets, you can always take the help of Euler's phi function to see at least if you are getting the required number of elements. So what I mean by that is this. So what is our modulus? 40. And what is this? This calculates the number of integers, positive integers less than 40 and relatively prime to 40, because the prime factorization of 40 is this. So there is a formula like that, right, for calculating the phi value of an integer. Four over 5. So this is 16. Are we getting 16 elements? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yes. And in this, our subgroup is the cyclic subgroup generated by 3, and its elements are these: 1, 3, 9 and 27. Okay. Now one can calculate that the elements in this factor group are 1 3 9 27. Then 7. Here also you see you have 16 elements and the order of this subgroup is 4. So how many elements will there be here? 16 divided by 4, which is 4. So just like that one, here also you will have 4 cosets. So you have to multiply, and in this case the binary operation is multiplication modulo 40. So when you multiply all these elements by 7, that is the operation, and when you do that you get these numbers: 7 21, then 23 29, then 11 3, and here the numbers are 11 33, 19 17. Also I have maintained the order of these elements in these sets. By that what I mean is that 7 times 1 is 7, 7 times 3 is 21, 7 times 9 is 23 modulo 40 if you calculate like that. So that order I have maintained for your convenience. And finally we have this one, 1339, then 37 and 31, and you can verify that these 4 sets form a partition of this. So they are non-empty, of course, you can see that they are mutually disjoint and their union is the entire group. Okay, now we come to the now we write the table. That's it. So because here also we have 4 elements, so we can modify this table itself. It has started to rain a little. And there is some rumble of thunder also. It's nice, the temperature will go down a bit. There is no point erasing the entire table and then creating another one. Okay, so we can do it here itself. Just have to change the elements. So the first one is, these ones will be easier to write. 7 3, then 11 3 and 13 3, and here also this group is going to be abelian because there are 4 elements. The first row and first column again like before. Seven 3, 11 3, 13 3, and then 3 13 11. So this is 13 and this is 11, and then 11 13 3 7, 11 13 3 7, so this is 7, so that means this is going to be 3. So that is the group table for the second group, and that completes this solution. Okay, now let's see the next one. Find a non-abelian group G such that there are two parts which have two requirements. The first one is this. This factor group, the factor group of G by the center of G, is abelian. Is it abelian? Yes. And the second one is G is infinite, but this factor is finite. Okay. Now the author has considered this group. One group itself suffices for both the things, both the parts. Consider the group G, which is the direct product of the dihedral group and the additive group of integers. Note that the center of G is equal to the center of the dihedral group times the center of the additive group of integers. You should understand that this identity is true not just in this case but in any such direct product, and it's extremely straightforward to prove. So what I'm saying is that if G and H are two groups whose direct product you have considered, then you have this. You just use the definition of center, the definition of direct product of groups. It's absolutely straightforward to show this. Okay, so I'm just assuming that this is something we already know, and now this is something we know, and it is, this center is nothing but that cyclic group generated by the rotation R180, and this is the group itself. Why? Because this group is abelian. Note that in this direct product, this is abelian but this is non-abelian. So the entire direct product, that is the entire group, is non-abelian. And we can see that also because the center has turned out to be this subgroup which is not the entire group. So G is non-abelian and this is the center. You can write that here. Hence, G is non-abelian. Okay. one can verify that the order of this group is 4. This I leave to you to understand why this is 4. You try to think of the, so what is it that you have to figure out here? Here G is this direct product and its center itself is also a direct product of two groups. So in this factor group, you will be looking at cosets of this subgroup by elements coming from here, and you will have to understand that 4 elements only will be there. Okay, this part I leave to you. So what is the ultimate conclusion from all of these things? This is abelian. Why? Because its order is 4, just like before. Okay, any order of any group of order 4 is abelian, and here G is obviously infinite, and that infinite nature of G comes from this second factor. Because of that, G is infinite. However, this of course is finite because it has only 4 elements. So you can write the final conclusion in your own words that we are having these things in this example. Okay, so let me just complete the solution like that, and let us see another one. So this is going to be 14. It looks somewhat confusing at first glance, but once you think of it, it's nothing major. Show that an element of the factor group this is or has finite order if and only if it belongs to or it is in this set. You understand what this factor group is. Here the original group is the additive group of real numbers, and there we are considering the additive group of integers as a normal subgroup. It is normal because the original group is abelian. Now it's about the elements in this group having or not having finite order. Okay, so let's see the solution. So let us consider any element here. Let this coset, we are writing it, the coset not as RZ but R plus Z, because plus is the binary operation. Where of course R is a real number. Strictly speaking, this need not be written separately, but just for our own understanding, there is no harm in writing this. Once you write this, it automatically means that R is coming from here. I mean, in usually how we write things, that's what it means. Okay. then for any positive integer n, we have the following equivalences, means equivalent statements. So what I am trying to write here is this. The element r plus z having finite order means the existence of such a positive integer such that this nth power of r plus z in this group is equal to the identity element in this group, because that's the condition for having finite order. Okay, let us now see what this condition becomes. Keeping in mind that this power we are calculating in the group in which the binary operation is addition, or actually it's not ordinary addition but something derived from ordinary addition, in which when you calculate the power nth power of r plus z, you add n copies of r plus z, and that ultimately gives you nr plus z, not r to the power n. It's just a matter of notation, okay? Which is equivalent to what? Now this will be the case if and only if nr is an integer. Okay, now here lies everything. If r is a rational number, right, then r is of the form p over q, where p and q are integers and q is non-zero by the very definition of rational numbers. So in that case you can choose n to be q, so that qr is p, and that definitely belongs to the set of integers. So that means if our real number is a rational number, in other words, if our r plus z is coming from q slash z, then r plus z has finite order. That order need not be cube itself, but there is some finite order. Conversely, if r is not rational, say r is irrational, and you are forcefully assuming that even in that case nr is an integer, then what would go wrong? Say r is an irrational, but still nr is an integer. Some integers say m, but then because you are considering a positive integer n, so you can divide by n, but then r has the very form to be a rational number. It then becomes a quotient of two integers, but we have assumed r to be irrational, so that is a contradiction. So that means if r is irrational, then such an n does not exist. And this part I hope is clear enough so that you can expand this and write it as an argument on your own. And because of these things, we have the solution. So I am leaving this part unfinished to you so that you can write it and complete the solution. You have the full idea here. You just have to write it nicely, all the arguments in order, and complete the solution. So with this, I end the video for tonight. Tomorrow also we have an upload, and tomorrow as usual we are going to go back to analysis. So see you tomorrow with analysis. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.